let's try to solve this problem here. A 60 kg man stands on a scale in a moving lift. Well, it's a lot of object here, so let's try to draw it out. We have a 60 kg man, and this 60 kg man here is standing on a scale. So let's draw something rectangular to represent the scale. And this scale here is in the moving lift. So this will be the lift. I assume, yeah, something like this. Then yeah, there's a cable hanging because it's a lift, it might goes up and down. Okay, so this person here is 60 kg. If g here is the acceleration due to gravity, which is the 9.81 that we know, determine the scale reading when the lift accelerates upwards or downwards or constant speed. Okay, so this is something about physics. If you see the word scale reading, right? Scale reading, yeah, it's a scale that you have at home. You stand on a scale, then it gives you how much mass you have, right? So, but this scale reading here, it will be reading the you'll be showing the normal force that acts by the scale on the person. Okay, so the scale reading here is actually just a normal force. Normal force acted by the scale on the person. Okay, so this is how a scale works. Because you have a scale, right? You step on the scale, you are exerting a normal force on the scale. Okay, because the normal force is touching you, therefore you are exerting a force on the scale. So the amount of force that you exert on the scale will be equals to the normal force acted by the scale on the person. Okay, the person exerts a force on the scale, and that force should have the same magnitude as the normal force acted by the scale on the person, because that's Newton's third law. And that normal force acted by the scale on the person will be what's being shown in your scale. What's the should be the reading that is shown in the scale. Okay, so if now we know the situation well already, we know we want to determine the normal force for each of these situations here. So let's try to draw a free body diagram, then we will try to look at what happens if we are in these three different scenarios. So the free body diagram, our focus should be the we are saying acted on the person, right? So our object of interest will still be the person over here. So let's use a dot to represent the person. Again, we'll use dotted lines to have to show our axis. Since the leaf will be moving up and down, I believe we will have something like this for our axis. Let's call this X, let's call this Y. Okay, now let's ask ourselves a 5 question. Does this person here has mass? Yes, it has mass, so there will be weight exerted by the earth on this person over here. Is there any ropes attached to this person over here? Our object of interest is the person, so you don't look at this rope, you look at any rope hanging around the person. Well, no, so that means there is no tension. Okay, next thing, is there any force being explicitly stated in this situation here? Do you see anything saying that there's a force acting on this person? Do you see any force in this diagram here? No, so there's no external force. Next question, is this person here touching any surface or touching any object? Yes, this person here is touching the scale. So because it's touching a scale, there will be a force exerted by the scale on the person, and that force is a normal force. So your normal force should be pointing upwards because it should be perpendicular to the surface of the scale. Perpendicular to the surface means something like this. So it's either up or down. Now try to think, if the scale is supporting, if I'm a scale and I'm supporting a person on it, I need to push the person, so I have to push upwards, right? If I'm downward, then it will be pull already. So the normal force should be pushing upwards. So this should be the normal force. Then the last question is there any rough surface being mentioned here? Or is there any rough surface in this situation here? Well, the rough surface, it's not relevant to this situation here because yeah, you are not attempting to slide or something like that. Okay, so there'll be no friction involved in this situation. So that will be our free body diagram. Our free body diagram, we have a normal force pointing upwards and weight pointing downwards. Okay, so now that we have known our free body diagram, let's try to analyze what will happen to the normal force at these three different scenarios. Our focus is to determine the normal force because this normal force acted by the scale on the person will be the scale reading for our situation here. Okay, so let's look at question number 1. For question number 1, it accelerates downwards at 0.2 g. 0.2 g here is not 0.2 gram. This g here is 9.81 acceleration due to gravity. Okay, so if the acceleration is pointing downwards, let me put it in red. Acceleration is pointing downwards, then we will take the downward direction as a positive side of the y-axis. Okay, we follow the direction of acceleration. The direction of acceleration will be the positive side of the axis. So in this case, since our acceleration is pointing downwards, we say that we are taking downward as positive y. Okay, taking downward as positive y. So now if you want to build your equation, you'll be building a Newton's second law equation, right? Because there's acceleration involved. There's acceleration involved, there's net force, so sum of F is equals to ma. So in this case, it's sum of F in the y direction is equals to ma y. But for this case, we take downward as positive, so we will take what's positive, w, minus what's negative. Negative should be upward in this case, so we are minusing n, and this should be equals to ma_y. So now our focus is the normal force, as we mentioned just now. So if we make the normal force as our subject, then what we have here will be weight minus ma in the y direction. So this will be mg minus may. Let's do our substitution. Let's factorize out the m first. Probably this way is easier. Factorize out m, then g is g, then ay here is 0.2 g, right? And we write down 0.2 g. Okay, you might be wondering whether this downward, does it mean we need to put negative 0.2 g or not? Well, technically, if we keep the initial kind of axis, which y is pointing upwards as positive, downward as negative, if we keep it that way, then the acceleration has to be negative. But now, since we are taking downward as positive, then now this downward here will be positive. So there will be no negative sign in front. So your A here, you'll be substituting 0.2g instead of negative 0.2g. Okay, so now we are done with that. We will substitute in everything. 16.0 times, this is 0.8g, right? Times 0.8 times 9.81. Then what will you get for your answer? You will get 471 Newton. So this is the reading that will be recorded on the scale when this leaf here is accelerating downwards at a rate of 0.2 g, 0.2 times 9.81. Okay, now what if we are in situation 2 where we are accelerating upward instead? So now this situation, we will need to change. Our acceleration is pointing up right now. So if our acceleration is pointing up, then we'll be taking upward as positive y. So to avoid any confusion, we should actually restate again which side do we pick as positive. So we are taking upward as positive y. So downward now will be negative y. Upward as positive y. So if that's the case, then sum of Fy is again equals to may because there's acceleration, there's net force. So now we'll be taking the positive side, which is pointing upwards, and minus the negative side, which is weight pointing downwards. So now if you move around your equation, you get n is equals to w plus may instead. So this will be mg plus may. Then this will be factorizing out mass, then you get g plus 0.2 g. Okay, now upward here, it's a positive direction. So now we'll be writing 0.2 g instead of negative 0.2 g. it depends on where we pick as our positive. If we pick upward now as positive, upward, positive, then upward, positive, downward, positive, downward, positive. So this one is positive. Okay, so it depends on where we define as the positive x or positive y. Okay, so we continue. So now this should be mass 60.0 times 1.2. 1 plus 0.2 is 1.2 times 9.81. So for this, you'll get your N to be equals to 706 Newton. So this will be the reading recorded on your scale if the lift is accelerating upwards. Means by, the acceleration is pointing upwards. Okay, so that's the second scenario. Now let's move on to the third scenario where you are descending but at constant speed. Means by you are falling but your speed remain constant. Let's say initially the lift is falling at 3 meters per second, but 5 seconds later it remains at 3 meters per second. It doesn't speed up, it doesn't slow down, but it's going down. It's going down but not speeding up, slowing down. Okay, that's the situation in scenario 3. So for this situation, we know that constant speed, then lift move in a straight line only, right? So you are not changing direction, you are not changing magnitude of your velocity. So in that case, you can call it a constant velocity situation. So this is a dynamic equilibrium situation because initially same speed, same direction, final same speed, same direction. There's no change in speed, there's no change in direction. So if that's the situation, you need to analyze it using Newton's first law. So Newton's first law, you don't need to define where is positive, where is negative, because you take what side minus what side, you still get 0. Okay, so in this case, we take N minus W equals to 0. You can take W minus N, no problem. And for this case, N is equals to W, and that is equals to mg, and that will be equals to 60.0 times 9.81. Then what should you get for your normal force? You get 589 Newton. Okay, so this will be the reading that you read, that you see in your scale if the lift is going down but with a constant speed. It's why no speeding up, no slowing down. Okay, and again, this is also the scale. This is also what you read on the scale if you put your scale at a normal situation. If you record your weight at the normal situation, this is what you get. Okay, because normally you are at rest, right? You are not accelerating upwards or downwards, and this will be the reading that you read. But one day, if it happens to put your scale in the lift, then you accelerate upwards, and this is what you get. If you are accelerating downwards, then this is what you get. Okay, accelerating upwards, you get heavier. Accelerating downwards, you get lighter. Okay, so that is what you observe if you try to measure your weight in an elevator, in a lift, going up or going down.